Hey everyone, welcome to this explainer. Today we're doing something really cool. We are taking abstract mathematics, specifically concepts straight out of the Cambridge syllabus, and we're making them completely, tangibly visible. We often think of algebra and geometry as just numbers trapped on a whiteboard, right? But they are actually the invisible blueprints of the physical world all around us. Let's start with something we all care about, money.
So imagine this. You've got $2,500 to invest, and you lock in a pretty solid 4% annual interest rate. You just leave it alone. The big question is, how long exactly is it going to take for that money to double to $5,000? It's a totally real-world scenario, but we don't have to guess or just wait around for decades to find out. Math basically gives us a time machine here. And the answer? 18 years. Using logarithmic equations, we can calculate this perfectly. Because the formula for compounding interest asks us to solve for an exponent, we've got to use logs. So we just take the log of 1.04, divide the log of 2 by that number, and boom, it spits out 17.7. Since interest is calculated at the end of the year, it takes exactly 18 years to double your cash. And honestly, this is just the tip of the iceberg of what these equations can reveal.
Here is our quick roadmap for today's explainer. First, we'll look at modeling the real world with exponential equations. Number 2, we'll see compounding interest in action through a financial race. Third, we're transitioning into physical space with geometry and paving design. And finally, number 4, we'll explore some wild optical illusions with the math of curve stitching. Let's get into it. Section 1, modeling the real world. How exactly do we take messy, unpredictable real-world events like nature and shifting temperatures and somehow box them into clean, predictable mathematical models? Let's look at a flock of flamingos arriving at a lake over a 10-day period. Our exponential model here is p equals 3 times 1.8 to the power of t. P is our flamingo population, and t is our days. With just the single line of algebra, we can track the growth of the whole flock. Say we want to know exactly when there are 40 birds at the lake. We literally just plug 40 in for p, solve for t, and we've got it. The math lets us scrub forward and backward in time, which is just incredible. All right, let's apply this to physics. Imagine you've just taken a hot pan of water right off the stove, set it on the kitchen counter, and it's cooling down. The formula capital T for temperature equals 76 times 1.4 to the power of negative t plus 21. That models this exact cooling process minute by minute. That negative exponent is brilliant because it perfectly illustrates how the temperature drops over time, slowing down as it gets cooler. If we plug the first 6 minutes into a data table, we can chart the exact temperature drop. And by plotting these results and drawing a smooth curve, we're not just looking at abstract data anymore. We've got a visual tool. We can literally trace a finger along the curve to estimate exactly when that water is going to hit 55 degrees Celsius. But okay, here is absolutely my favorite part of this equation. Consider this prompt. Find the room temperature of the kitchen. Now, how could we possibly know that from a formula about a hot pan? Well, think about it. As time goes on to infinity, that hot water is eventually going to cool down until it perfectly matches the room. In our formula, that 76 times 1.4 to the negative t will eventually shrink all the way down to 0. And what's left? That constant at the very end, plus 21? That brilliantly tells us the ambient room temperature of the kitchen is exactly 21 degrees Celsius. It was literally hiding in the math the entire time. Section 2, compounding interest in action. Let's see how this builds as we shift back from physics to finance, watching exponential modeling create a really high-stakes race. We have a classic tortoise and hare situation on our hands here. Take Pedro, for instance. He deposits $2,500 at a very healthy 5% compound interest. Meanwhile, Marta starts with a massive advantage, $4,000, but she's only getting 2% compound interest. Now, assuming neither of them withdraws any money, we are witnessing the great investment race. So, the burning question is, when exactly does Pedro overtake Marta? Marta starts with $1,500 more, but Pedro's money is growing faster. By writing a formula for the total amount after n years for both accounts, we can set them directly against each other. It's this algebraic collision course that proves, over a long enough timeline, the rate of compounding interest will always beat the starting principal. Always. Section 3, geometry in paving design. We're going to shift gears pretty dramatically here. We're moving from exponential math over time directly into physical space. We're going to see how algebraic rules dictate physical shapes out in the real world, specifically laying down a driveway. Now, what's really fascinating is the breakdown of a paving design. If a company is block paving a driveway that's exactly 1 unit wide by 5 units high, the design physically breaks down into this exact ratio: 10 equilateral triangles, 4 rhombuses, and 2 isosceles triangles. But the real question is, what if the homeowner wants a 2 by 4 driveway, or a massive 10 by 20 driveway? How many blocks do we actually order? We definitely don't want to just guess, and we for sure aren't going to sit there and draw out a massive 20-unit driveway by hand just to count the blocks. No way. Instead, we apply the scientific method. We draw a few small test designs, we meticulously count those block shapes, we log the physical results into a table, and finally, we extract the mathematical rule. Here is the resulting data set. By mapping the dimensions like our 1 by 5 design against a physical count of 10, 2, and 4, we create this structured table. Once you do this for a half dozen different sizes, these totally invisible patterns begin to emerge right out of the grid. And the data reveals something really beautiful. The number of isosceles triangles, I, is strictly related to the width, W. The equilateral triangles, E, are tied to the height, H. And the rhombuses are? Well, they're determined by a combination of both width and height. By turning these relationships into simple algebra, a contractor can instantly calculate exactly how many blocks to order for a driveway of absolutely any dimension. The algebra literally becomes the architect. Which brings us to section 4, the math of curve stitching. In this final part, we'll see how strict, rigid, straight lines can actually trick our human eyes into seeing beautiful, sweeping curves. Curve stitching produces this really cool curved effect, but mathematically, every single line used in the construct is perfectly straight. It's basically a geometric optical illusion built entirely on coordinates and line segments. To build a simple 3x3 curve stitch, we just map coordinates. Imagine an L shape. One axis has letters, A, B, C. The other axis has numbers, 1, 2, 3. You draw a straight line connecting point A to point 3, then point B to point 2, then point C to point 1. You are systematically crossing these totally rigid lines over each other. So the crucial takeaway is what happens when those lines actually cross. This basic 3x3 curve stitch produces exactly 3 points where the lines intersect, and it traps empty space to create exactly 6 enclosed regions. And it happens perfectly every single time. It's an absolute geometric guarantee. But what happens when we scale this up? What if we do a 10 by 10 stitch, or, I don't know, 100 by 100? Well, because the math is governed by completely predictable formulas, the number of intersections and regions changes in a perfectly patterned way. And this isn't just a fun little drawing exercise. This mathematical scaling is exactly how artists, string art creators, and even architects building massive bridges create vast, intricate, sweeping curves out of perfectly straight steel beams and cables. We've definitely covered a lot of ground today. We tracked flamingos, cooled down boiling water, raced to bank accounts, paved driveways, and literally stitched curves out of thin air. It brilliantly illustrates that mathematics isn't just some boring subject. It is the underlying source code of our entire reality. So I'll leave you with this final thought. If math governs everything from the cooling of your tea to the optical illusions on a canvas, where else is algebraic magic hiding in plain sight in your daily life? Keep your eyes open. Thanks so much for joining me for this explainer.